Sorry, Mani, for the delay in timing, but over to you. Thank you.
Thank you, Nahina. Can you hear me and can you see my slides?
Yes, we can hear you. We can see your slides too.
Fantastic. So what I will be presenting today is really focused on the teaching of chemistry. And my name is Mani Naiker. I'm the lecturer in chemistry here at CQU Rocky. Lara Wakeling is a former colleague of mine from Federation University in Australia. She's a senior lecturer in food science and a prominent academic there with the quality of learning and teaching. And Joel and Janice are my aged postgraduate students who are involved in teaching some of the chemistry pracs that we implement here. So without wasting any more time, the first thing I want to make it obvious to everyone, if you haven't realized before, obviously if you're not from a science or pure science discipline, chemistry is a difficult subject to learn and teach. And this is more compounded by the fact that a large chunk of the enrollments or the students we take on at first year level have had no prior knowledge of chemistry, or even if they had done chemistry, it would have been, long time ago, as and these are usually the mature age students that we take on. So they are here not to mostly become chemists as such. So in other words, they're not here to largely get a Bachelor of Science majoring in chemistry. There's a very small group that does that. But majority of the students that we teach intro-level chemistry are doing it because it is a service course to their programs or courses like food and nutritional sciences, medical sciences, education, and so on. So first of all, they say, look, I'm not going to be a chemist. Why are you guys teaching me chemistry? I'm here to be a paramedical scientist, not a chemist. But the basic issue is that chemistry forms the basis of most of these pure science disciplines or programs. So as a service course, they have to do at least 1 or 2 intro-level chemistry. So there are traditional lectures, tutorials, and of course, lab classes are a very key component of teaching chemistry. Without laboratory classes, it will be pretty much a lot of void will be existing. So that is one area we can get these students to engage with the course materials. Because of the practical nature of a lab class, students are more relaxed. They feel they can take ownership of things. They're doing things practically. So they feel that they're actually engaging more than they're placed on a lecture, in front of a lecture, or in a tutorial for that matter. So what I'm trying to deliver today is an approach of teaching lab classes that will increase the engagement even more and capture some of these students who are lagging behind and make them their perceptions change towards chemistry, so they can at least get through the intro chemistry they're doing and move on with their programs. Traditionally, all universities have been using the recipe style of teaching in the lab. In other words, you give them instructions. You say, today you will be analyzing vitamin C in fruit juices. Here are the 10 step-by instructions. The material is over there. Go and repeat these instructions. Get the data, write it up, and off you go. But that does not engage students as much as we would like. In the recipe style of teaching results in lower student engagement, which then results to high attrition rates and of course high failure rates. And these students get stuck with these service courses when they're doing well in other aspects, other units, so to speak. So also the recipe style not only lacks in engagement, it also doesn't allow developing the students' independent thinking and problem solving skills, which are some of the key graduate attributes that many employers would be, looking for in their employee. So to improve all this, what we did was we adopted a inquiry-oriented learning, IOL, approach to teaching chemistry in the lab environment only. Okay, so IOL, inquiry-oriented learning, is also called inquiry-based learning. They are the same things. So very quickly, what happens here, you ask a question, any question. What is the temperature today, or how shall we measure temperature? As an example, you create a hypothesis Remember, this is all within the lab environment. You create a hypothesis, you investigate it, you construct new knowledge, you discuss, reflect on what you have found, and that finding will allow you to generate another question. And you could keep going until you offshoot from this as a tangent, you get out of this cycle, and you take this new knowledge and idea and as part of your graduate attribute, and at this point, you are out in the real life implementing what you have learned in a different approach towards your learning. So this table here gives you the different styles of lab teaching. You've got the recipe-based. Here, the procedure is given, student engagement is low, inquiry, high, and problem-based, which is another way of engaging students. The student engagement is high. So what we have chosen is the inquiry approach, so inquiry-oriented learning towards teaching students in the lab. So, just a bit about what we did. So this study was taken a few years back when I was at Federation University in Australia, and based on that result, we are trying to implement the same approach here at CQU next year. So just let's look at what we did. So we had 73 first year students enrolled in an introductory chemistry course, Chem 2 at Fed Uni semester 2. So at Fed Uni, there was Chem 1 in first semester and Chem 2 in second semester. So this cohort had previously learned basic chemical skills in semester 1. So we did not try this new approach straight up as soon as they came into the first year of the program. We let them go through the first semester on the traditional style. They get to learn some chemical analysis skills. In semester 2, we implemented the new approach. So how was the new approach implemented? What we did was we divided them into groups of 5. So if we had a group, 30 students, there would be groups of 5 or 6. And then each group was given a task right at the start of the semester. So a task could be a question. It could be a little project. For example, if you look at my screen here, we got lemon on the left, my left, and orange on the right. They're both from the citrus family. So the question could be as simple as, go and find out which has got more vitamin C. As simple as that. Both is expected to have vitamin C, but which one has got more? That little question such as that now starts to get them thinking. And that's where inquiry, investigation, and all of these things follow on, right? Another example is we give them Sprite, Pepsi, Fanta, and Coca-Cola. We know for sure, these manufacturers use preservatives there, and it's benzoic acid. We're just asking them which one has got more benzoic acid. A simple question like that at an intro level starts to get these students who don't usually want to engage or are fearful of chemistry, starts to make them think, right? And they are working within a group. Each group has a team leader. They take the ownership of the project now or the task. They devise their own methodology, their workload distribution, of course, periodically confirming with the demonstrators and the instructors to make sure they're on the right track. And once the demonstrators are happy with their approach and their project design or the way they're going to unfold this experiment, we instruct the lab techs to make the materials and equipment ready, provided on the day. So the students will also give a list of methods, materials, reagents, chemicals, equipment they need. So we don't do all of that. They design everything. We just say, yep, it's good to go. And basic thing is, doing this way, the students take ownership of the project. Suddenly they forget about, the chemical formulas of sodium sulfate and sulfuric acid and balancing equations and all that. And they say, oh, oranges and lemons. This is pretty realistic. I go and shop every day. This is always in my kitchen. Let's find out, right? So once they get everything ready, they do this project on their own, of course, supervised whilst we're watching them. They present their results and they write about it. So after the semester ended, towards the end of the semester, when this task was finished, we gave the students a survey instrument adapted from Reiner et al. It's right at the back, the reference. And of course, we had the ethical approval from the university. We got 64% of responses, which is not bad for the total classes. And Let's see what the results showed. So because the students had in first semester a traditional style of lab teaching experience, second semester they had a new approach. They were in a great place to compare the new approach to the old. And of course, we got 85% positive output here, saying that this new approach was interesting and enjoyable. And that's really key for me, you know, teaching chemistry for so many years now. And if we can't get students interested, if they're not going to buy in your discipline, what you're trying to teach them, they will just hang about, try and exist. Okay, so 85% said this was interesting and enjoyable compared to semester one. Self-guided investigations were something new and unique for them. Exposure to experimental research, 83% felt by using the IOL or investigative approach rather than the traditional recipe style, they had more exposure to experimental research and what scientists actually do rather than just coming and following a set of instructions. This is really key, especially for those who wants to go and do research down the track, you know, honors and masters. Trying to get them exposed to some form of experimental research from the outset can only make them a better graduate who can take postgraduate studies, or for that matter, work in a research lab. Lab equipment skills. Now, this is important. In a traditional recipe-based lab, they will still use equipment, but here they went and worked on which equipment they have to use. So they did a bit more behind the scenes work, which we or the tech staff usually do for them. I'm sure that would have given them some positive engagement towards the learning of chemistry. Teamwork, very, very important, especially it is one of the key pillars of graduate attributes that employers recommend now. Having myself worked in a commercial sector, I do in industry appreciate how much employers are seeking in their employees to be able to work in a team environment in a collegial manner. Critical thinking is always important. That brings in your investigative approach, and that's a life skill, so to speak, you know, in your workforce and so on. So some very positive output or perceptions of students when they compared and placed themselves in the situation of the new approach and the old approach. And all of this can only mean that we are increasing student engagement. This may not necessarily make them all get HDs, but it makes them satisfied and makes them interesting towards this subject. And the more they open up, the more they will pick up, which they would not if they just sat silent and say, oh, this is all, I'm instructed, I've got no ownership of what I'm doing, and I'll just tag along. Some of them would not have passed, but taking the new approach, they might have a chance of getting over the line now. So the results that we got, we did a bit of statistical analysis very quickly. We did k-means cluster analysis. Whilst, this is interesting, whilst majority, 75% and more of the students had very positive outlook towards this new approach, we still had a small 11%, which is less than a quarter, they had negative attitudes towards it. Their mean score was 2.9, 0 being negative, very negative, and 5, of course, being very positive. And we believe the difference was predominantly related to theory and planning concepts such as critical thinking, observation, recording, data analysis. What this tells me that this 11%ers, this small group, would not have liked chemistry either way, either old style or the new style. But from our teaching perspective, going forward, this small group is more important. These students will need to be given more support, more scaffolding learning, so they are not left behind. We've got to eventually bring this 11% out, you know, negative perception holders up to the same wavelength as those who perceive this new approach. Well, majority of them see it being good. We also did some exploratory factor analysis on the questionnaire and identified 4 major aspects of students' positive attitudes towards IOL: theoretical aspects and planning, right, managing their work, support and guidance, investigative research, and lab skills. This investigative research aspect brings in the inquiry, to question, to critically think, going back and forth until you find the right answers. So all of these, again, will greatly impact the graduate attributes that the students will gain from when they graduate. So in conclusions, firstly, we would like to suggest some improvements. More guidance and assistance with understanding the specific assigned problem is probably one way we could help those 11% or that cluster of 20, a quarter, which found it negative. Rather than giving them a topic, we can ask students to choose their own topic from a list, as long as it's within the viability of making sure it can be executed in a first year lab. And maybe a smaller group, two to four people, so that everyone gets opportunity to be more hands-on. That's always interesting fine line that we have to play with how many demonstrators we got, how much equipment we got, X, Y, Z. The challenges are many, as anything you try and implement in the first instance, and it's work in progress. It will evolve, it will get better. One of the things is the entire teaching team, and I must include the lab staff, they must come on board. I have to sell this to everyone, all the stakeholders. I can't just get all my demonstrators and say, look, we're going to do an IOL approach this time around. I've got to make sure that they are well trained. The tech staff, there's more tech staff, because in any one day we could have multiple projects going on, because they're all doing the different things. So there's a few things we could tinker with, but so far, lucky enough for me, all the stakeholders that I've dealt with have been very positive towards this approach. Finally, groups must be closely monitored to ensure they are on track and all members are participating. Again, that comes with more well-trained and experienced demonstrators who are comfortable in this new approach compared to the way things have been done previously. So that was what we have done. So what we're going to do now, we are planning to introduce this approach to second year laboratories at CTU now from term 1 2020. So this will be advanced organic chemistry taught for the first time. And we have already started planning to implement what we have learned from our experiences at Fed Uni to a second year lab situation. So let's hope this also gives us some new, we'll be surveying this as well. We'll be keeping a tab on this, and we will always try and tweak with it and improve as per feedback we get. As I said, we would like to thank academic staff, lab technicians, demonstrators, and students at Fed Uni for making this work possible. And we would like to thank our current staff here who are very positively engaging with me in view of implementing this next year. And I would really like to thank, should be thanked here, Dr. Ryan Kift, our head of college for science and sustainability, and Dr. Tanya Signal, the deputy dean research for our school, for their fantastic support, in helping me implementing this learning approach at CTU next year. I mean, without their support, some of these things would be impossible, because when you are trying to do something for the first time, you've got to build the capacity, and building the capacity sometimes requires some in-kind contributions, some financial aid, all sorts of things going in. And sorry about that. We must have done something well to convince Ryan and Tanya to come on board. So far it's all looking good. And we are just raring to go next year and try and get this up and running here at CTU. And finally, the results are presented here is from one of our publications, Evaluation of Group-Based Inquiry-Oriented Learning in Undergraduate Chemistry Practicals, was published in International Journal of Innovation in Science and Mathematics Education. So if anyone is interested, they can go and look at that, or just email me, I will flick it around. Thank you, everyone. Any questions?
Thank you so much, Mani. It was a very interesting thing, and really excited to see the results. And good luck to you to implement it next term in CQU. Let's take some questions for Mani. And before that, just wanted to let every attendees know that thank you so much for attending. And we have an evaluation link that has been posted on the chat box. So everyone, if you could please take some time to go there and click on the link, and please evaluate and put your feedback for the session. And thank you again. And any question for Mani?
Can I ask a question to Mani?
Sure,
Yes.
Mohammed.
Hi, Mani. Thank you for your presentation. It's very interesting topics, inquiry-oriented learnings. I'm just wondering, you done research on your discipline chemistry. So, do you have any suggestions or frameworks that you're gonna develop that we can apply in our business educations? Or, for example, I'm an accounting lecturer. So, how can we apply these in our disciplines? Do you have anything to do for future?
Yeah, well, understandably, our focus has been on chemistry because that's what we try to improve engagements of students with. But from literature and from my reading, there's nothing to suggest that it cannot be applied to other disciplines. For example, if you are in an accounting or economics discipline, it might be better suited at a level where you are giving students projects, like case studies or research projects. Uh, maybe not in the first year where you will be enhancing them with a lot of theoretical concepts to get them ready for some project case study related scenarios. Maybe there you could try this approach and say, look, I can't think of a problem, but for example, the impact of not having international students in the higher education sector, an economic or business question, and that is the question, and they can go back and start to hypothesize about that question and what do they think are the positive and negative answers they can get. And then they do some investigations. What are the other countries doing? What are the other universities thinking? And you see, you're going around in a circle, and then you'll find an answer or even half an answer. Then you'll ask more questions about it. Then you'll go at the sub level until you are at a point you say, yep, I've got a definitive answer here which can be accepted or justified. So I think it can be used, but you've got to think outside the box how and when it should be implemented.
Mm. Thank you. Yeah.
I have a question, Manny. Thank you so much for your presentation. It's really interesting and very informative. You did pinpoint about the group challenges
Yep.
and the need to have a close monitoring process or something like that. Could you just give us more insights about what challenges are we talking about here, and why you think group assessments or group work needs that particular attention, especially with regard to online setting that we are in now?
Yeah, so it's difficult for me to comment on the online group work scenarios. I mean, the work we have done is purely in the lab. So for my unit next year, everything will be online. The students will only come for 3 days, and that is the only time we will see face to face. And that's when I'm going to implement this way of teaching. What do you call chemistry practicals. Now, going back to group work, I think group work is important. We should continue to keep it, pushing forward. And while we're doing it, we should learn how to get everyone on the same page. As you can understand, in a group of, let's say, 30, they will all have different backgrounds and different abilities. And then you put them into groups of 4 and 5. Within the groups of 4 and 5, again, they will be more compounded with different abilities. So things like, like within the first few weeks, one, 3 of them out of 4 might think, oh, this fourth person is not coming to the party. He's not, not contributing. So those are some of the things. It has to be done on. I've done this approach 3 years in a row. Every year I had different issues with groups, and different groups within a year had different issues. So it compounds your work to keep on top of that. So you identify each group and where they're going, and then you say, okay, this group here, that they're going on well. They don't need much. They will come to me if they need help. But then other groups, you might want to prompt them, give them a bit of a push. So that's where when we're doing this kind of approach of teaching, we have more demonstrators. Let's say if we have, 8 groups in the lab, we will need at least 4 demonstrators, 2 to each group. So in other traditional style lab, for that many students, we'll only need 2 demonstrators. So those are some of the economics that we have to discuss with our, head of courses and our superiors to make sure that they're on board as well. So group work is fundamental. It hasn't distracted me yet, but I know it is always challenge. Even you say, okay, I've been doing it for so long, I know I can handle it. Next year, new cohort, new groups, there will be another set of challenges. You'll just have to, work it as you go through.
I've got a question, if that's okay.
Yes, Cheryl.
Great presentation, thank you. I always want to know more about inquiry-based learning. I've never actually done it myself. But I was wondering if, because you said a lot of students are from different courses, whether the questions that they answer are related to their particular course?
Well, that's something we would like to implement going forward, where we open up, like they decide something appropriate. And that will depend on the groups. We try and mix the groups. So, for example, we don't put all the food and nutritional sciences into one group of 4. You know, we mix it with education students, biomedical students. So try and make as mixed as possible, so that they all try and not be biased towards any one topic. So it's, you know, for example, when I said lemon and oranges, you know, it's sort of like, even if you are not food and nutritional science student, you are a geology student, the approach would be the same, where you go and look at 2 different rocks and see which one has got more minerals, you know. So it is at intro level, so we try not to make it the program or course specifics, rather general, so they got to get out of their comfort zone as well when we're dealing with this questions of and problems of this manner. Remember, these students had already done Chem 1 in first semester, so they've already acquired some theoretical understanding of chemistry, some lab skills. So any subject, any topic within the constraints of first year intro chemistry, irrespective to their program of study, they should be able to manage or try and manage.
Thank you.
All right, thank you so much, Mani, for the presentation, and thank you everyone for the for attending and for the great questions. And I would like to thank all the presenters for the very beautiful and informative presentations. Please don't forget to click on the link and provide your evaluation for the session. And we will see you all in the next session, maybe.